Welcome back to this video of electromagnetism. In this video, I'm going to discuss about a self-inductance and mutual inductance. So let me relate with the self-induced EMF and mutually induced EMF. Self-inductance also, if you look at this particular circuit here, it's a property by virtue of which it always opposes any change in the value of the current flowing through it. So in other way, we can define as the number of Weber turns produced per ampere in the coil. So given as L instead of E, I can write this as L is equal to N phi by I. So this is nothing but number of turns. N can be written as phi can be written as Ni divided by I into R. Okay, so this can be written as N square by, okay, R can be written as L by mu naught mu R into A, where I get cancels here. So R, we can relate R is equal to rho L by A, and R can be written as L by mu R, okay, mu naught into mu R into A. So when I replace that equation, where here mu naught is your absolute permeability and mu R is the relative permeability, and A is the area of the cross section of the electromagnet, and L is equal to length of the electromagnet. So this is, we call it as self inductance, that is L. Now coming to the mutual inductance. So mutual inductance, if you look at the second circuit here, whenever voltage is applied to one circuit, it not only links this coil, it also links this coil. So the current flowing here will produce the flux in this coil, and that flux also link in this coil. So this is called mutual inductance of the coil. So where we can write this mutual inductance, M is equal to N2 into d phi 1 2. I will relate this as phi 1 2. I'll explain it how it is phi 1 2 divided by di 1. Okay, so what I mean to say d phi 1 2 here, the flux which is produced by I1. Okay, let me write here. I1 is equal to phi 1. Okay, this phi 1 will not only link its own coil, that is first coil, that is phi 1 1. This also links with the coil second one. Correct, flux phi 1 will link with the second coil. See, this is how the suffix is given here. So phi 1 2. So this can be further written as same, no, N1. If I give it to the other circuit, this will be N1 into d phi 2 1 divided by di2. This is 1. Instead of the supply here, if I give the supply here, okay, then the current I2 flows here, and this I2 will produce a flux phi 2. I think now you can relate this. This phi 2 not only link its own coil phi 2 2, it also links with phi 2 1. So this phi 2 1 will be the mutual flux, okay, linking the other coil. So in the next slide, let us look on to the coefficient of coupling. So this is one derivation which is normally asked, how to derive the coefficient of coupling in case of electromagnetism chapter. So let us take two magnetically coupled coils A and B. So let us take coil A and coil B. So two coils is there. So the coefficient of self induction of coil A. So if I want to write self inductance of coil A, L1 can be written as suffix 1 refers to the coil 1 or A. Okay, let me take this as LA. Okay, so we can write this one as linking the coil. So first let me coil 1 and 2. Okay, better I can take this as 1 and 2 so that it is easy to write the suffixes. So coil 1 and 2. So we have two coil. So the inductance of the first coil is N1 square divided by 1 by mu naught mu R into A, and this coil we can write this one as L2 is equal to N2 square divided by 1 by mu naught mu R into A. Correct. So we have L1 and L2. Now, when current I1 flows in A, okay, when I1 flows in A, so it produces a flux phi 1, which is equal to N1 I1 divided by 1 by mu naught mu r into A. Okay, so the coefficient of coupling is the ratio of mutual flux to the total flux. Correct. So we can write coefficient of coupling, okay, K, okay, the coefficient of coupling is the ratio of mutual flux to the total flux. So with respect to first coil only we are taking, so it is the ratio of mutual flux to the total flux. So mutual flux is phi 1 2 divided by phi 1, and if I give the voltage to the second coil, it becomes K21 is equal to phi 21 divided by phi 2. So as the coupling is bilateral, both the side, okay, it is going to link. So we can write K12 is equal to K21 is equal to K. So where K is called the coefficient coupling here. So we can write phi 12 is equal to K into phi 1, substituting there, okay, and we can write phi 2 is equal to 21 is equal to K into phi 2. Okay, where I replace K21 and this one by K, and I am relating that equation here. Okay, so now after this, but we have mutual inductance M12. If I give the coil 1 voltage, it links the second coil, and we have a mutual inductance M12, that is N2 into d phi 12 divided by di1. And with respect to second one, if it is linking, so mutual flux can be written as M21 N1 into d phi 21 divided by di2. Okay, so now continuing with this, we can write mutual flux multiplying both one. So M12 into M21. Okay, M12 into M21 will give you, multiply this N2 into d phi 12 divided by di1 into N1 into d phi 21 divided by di2. So we can write M12 in this can be written as M square, like we have taken as K. Correct. K into K is K square. So M12 into M1, M21 as M. So M square. So is equal to N1 N2 and d phi 12 divided by di1 into d phi 21 divided by di2. So this can be further written as M square is equal to K square into N1 into d phi 1 by di1 into N2 divided by, N2 into d phi 2 divided by di2. So further we can write this as M square is equal to K square into L1 and L2, because this gives you L1 and this gives you L2. And this equation I'm getting in the previous slide. So I'm replacing N2 into d phi 1 2, this equations by this particular equation. Okay, so where I have written this one, okay, into d5 1 by d2. So finally we can write K is equal to, okay, M by, because taking the square root we get L1 into L2. So this is the coefficient of coupling derivation, where K gives the relation between self and mutual inductance, where L1 and L2 are called self inductance, M is called the mutual inductance. Now in the next last topic of this module is now energy stored in magnetic field. So what is the energy stored in the magnetic field? We know resistance opposes the flow of current, but inductance stores the magnetic field in the form of stores the energy in the form of magnetic field. So energy stored can be derived. Okay, we all know what is the induced EMF here. So induced EMF here is E is equal to minus L into di by dt. So we know this opposes the voltage. So we can write V is equal to minus E. Correct, because the induced EMF opposes the voltage. So this can be further written as V is equal to minus L into di by dt. Correct. So this becomes minus L minus into minus. So this becomes minus L into minus L into di by dt. So further it becomes V is equal to L into di by dt. But power supplied, we know P is equal to VI. Power supply is always P is equal to V into I. So this can be, if you substitute L into di by dt into di. Correct. Sorry, L into di by dt into I. Okay. That is I into I. So energy supplied E can also be written as energy supplied E is equal to power into time. Correct? No? Power into time. Energy supplied in a time. So power into time. So this can be written as power as L into I. Okay. Di by dt into dt with respect to time. So this gets cancelled. So we get E is equal to Li into di. But actually, the energy supplied for a change in current of di, changes from 0 to I. So we need to integrate this equation. So let us integrate this equation now. So where we have to integrate and get the equation for the energy stored in the magnetic field. So I will integrate this now. E is equal to, it is changing from 0 to current I, Li into di. So once you integrate, this becomes L into integral of 0 to I into di. I think now we can integrate this easily. L into integration of I is I square by 2 minus 0, because I'm applying the limits also directly here. So E is equal to half Li square. So this is the equation for the energy stored, and the unit is in joules. So I hope you have understood how to derive the equation for coefficient of coupling and energy stored in a magnetic field of an inductor. Thank you for watching this video.